now let's, having got these basic properties of U in mind, now let's go to something that builds a lot of intuition. Let's try to visualize these quadratic forms, right? We've written down this quadratic form over here, right? Over here. We've already done a little bit of visualization of this. Now let's look at it a little bit more carefully. Okay, so let's visualize. Okay, so I'm going to write it like this. And to visualize, of course, it's always good to start with the simplest possible case. So the simplest possible A would be a diagonal matrix, right? Now if, so let's assume A is diagonal. What is our running assumption about A? Symmetric, positive, definite, right? So therefore, can I say anything about A now? If I'm taking the special case that A is diagonal, can I say anything about the entries? They all have to be positive because they are itself the eigenvalues, right? So if I visualize this like this, right, and now I insert A to be a diagonal matrix, if I open up this X transpose AX, what do you think I'm going to get? I'm going to get a summation. So x1 here, x1 here. So x1 will multiply by what? Lambda 1 or A11 multiplied by x1 again. So what do I have left? x1 squared A11. Then I'll have x2 squared A22, right? So this is nothing but xi squared aii. I is equal to 1 to n. Right. Now, if this were just two variables, supposing n was 2, right? This would be what? X1 squared something plus x2 squared something. What is this the locus of? Supposing in 2D, this would be, let us say, x1 squared times 5 plus 2 times x2 squared. If you were to graph this, what will it look like? It's an ellipse, right? And these numbers are always positive because the diagonals are eigenvalues which are positive, right? So in general, this is going to correspond to what? An ellipsoid in n dimensions. Okay. So we can easily visualize this in 2D. I can draw ellipses on a piece of paper. If I want to visualize it in 3D, I can visualize like a chocolate eclair, right? It's a 3D ellipsoid, and then it, right? Beyond that, tough luck, right? At least normal human beings can't do it. So this was the case where A is diagonal, okay? So it's an ellipsoid. In which coordinate space? x1, for example, if I take the 2D case, in the x space, I'm going to draw ellipsoids, right? If I go on this ellipsoid, what is the meaning of this ellipsoid? If I walk on this ellipsoid, what is going to happen to the value of phi? It's going to remain constant. That's why these are called the contours of the function, where contour means the function value doesn't change as I go along it, like the map of a trekking hill. Okay, so now let's, having understood this, this is really obvious, you could have done this in high school, right? The next thing is, let's relax this assumption that A is diagonal. So let's say that A is not diagonal. Okay. What should I do then? If I try to write this summation, will I get something as neat and tidy as this? No, right? Because A is a full dense matrix and I'm just going to get everything everywhere. I can write it out. I'll get some expression which gives me no intuition. So is there something to help me out? I can use the Eigen decomposition. I have not used that so far, right? So if I try that out, Qx, which was x transpose Ax, and x transpose A is U lambda U transpose, U lambda U transpose X. Does this look like the previous case in some way, if we can bunch terms together, right? If I can group this and this, I have something similar, right? I have a diagonal matrix sitting in between. So supposing U transpose X is equal to Y, right? So implies what is Y transpose? X transpose U. So what happens to this expression? This becomes equal to Y transpose lambda Y. So in the space of, how will this look in the space of, in the y-axis space? So y1, y2, y3, if those are my coordinate axes, what is it? It's an n-dimensional ellipsoid in the y-axis space. So if this is my y1, y2, it's a regular ellipsoid over here. How does it look back in the x space? To get the answer to that, what is my key? My key is over here, right? So if U, so we wrote that X, U transpose X is equal to Y. So let's look at it like this. Right? This is X1, X2. Okay. So let us say that one of the eigenvectors, let's say U, let's say this is U1. And I know that the eigenvectors are orthogonal to each other. So U2 therefore must be like this. Okay. Now, looking at this expression, I can say that X is equal to U Y. If I left multiply by U transpose from here, I get this, right? So can I interpret this now? Supposing I give Y is equal to 1 0 0 0 like this. Okay. So 1 in the first entry, 0 everywhere else. What will pop out of this expression? The first eigenvector. U is a matrix. I'm multiplying it by the, what is the name for this kind of a vector? You'll read this word often in the literature. What is it called? Basis is a more general word, something more specific than that. Canonical basis. So when I stick this over here, what I'm left with is X is equal to, X1 is going to be equal to U1, right? That means if I'm, the y-axis, y1 axis corresponds to, in the x space, which axis? The U1 axis, right? That means if there were an ant walking along the y1 axis, in the x-axis space, where is the ant walking? It's walking along the U1 axis, right? So similarly, if an ant is walking along the along the y2 axis, it means in the x space the ant is walking along the u2 axis, right? So all that means is that that's how my contours look like. So the simple idea of rotation was very helpful, because if I directly took this objective function, there is no way I can group the terms together to realize it's actually just a rotated ellipsoid. Okay. But this angle is always going to be 90 degrees. This comes from the property that the eigenvectors of a positive definite matrix are orthogonal to each other. Simple. Any questions so far? All right, good.